welcome everyone. My name is Robert Schulze, actually. And I work as an engineering manager at Clickhouse. And today I will take a look under the hood of the new powerful JSON data type that we built in Clickhouse. As most of you know, the key feature of Clickhouse is its extremely high performance. Clickhouse is one of the fastest analytics database on the market. And of course, it's also one of the most popular databases. This slide shows some measurements for cold and hot query runtimes in ClickBench, our vendor-neutral benchmark for analytics databases. If you go to benchmark.clickhouse.com, you will find a dashboard with measurements of over 70 commercial and research databases. One of the key ingredients for Clickhouse's performance is its columnar storage. Let's say, let's say we create a table with some columns and corresponding data types. Clickhouse stores each column as a separate file on disk. This enables excellent compression ratios as the data of the same type and value distribution is stored next to each other. As a result, Clickhouse is able to scan and aggregate single columns at extremely high speed. And based on its columnar storage, Clickhouse processes the data using its state-of-the-art vectorized query execution engine. So, when you use a server with 4 CPU cores to run an aggregation query over table column 2, then Clickhouse will read only data from column file 2. Because we have 4 CPU cores, the data to process is split into 4 disjoint regions. And each region is processed by one of the CPU cores. Every core calculates a partial aggregation result, which is then combined into the final result. So Clickhouse leverages all available CPU cores by processing data chunks on multiple CPU cores in parallel. It also uses SIMD to process consecutive data elements in parallel. So with that, we could easily upgrade our server from 4 cores to 8 cores, and we would double the processing throughput for the example aggregation query. Now, let's say we also wanted to make Clickhouse the fastest analytics database for JSON data. What will we need to do? So imagine we have a table with a JSON column, and we insert a couple of JSON documents. The most intuitive approach would be to simply dump these documents into a string column. Let's see what it means for query processing on our server with 4 cores. If we have the same aggregation query as before, we could use all 4 cores in parallel. But what we could not do is load and process only the data of the single JSON paths that we like to aggregate. Instead, we would need to load all the paths in all the documents into the query engine. So basically, we would need to parse each document first and extract the values for the single JSON path we are interested in. And this is exactly how the JSON support is implemented in most databases on the market, and I can tell you that is very slow. So, to be the fastest analytics database for JSON data, we will need to store JSON documents in a true column-oriented fashion. If we do that, every JSON path will be stored in its own column file, allowing us to maintain the same level of performance that any other data type in Clickhouse has. Because then, with our server with 4 cores and the example query, we would access each JSON path independently, which minimizes the amount of disk I/O we do. Once a path is loaded, we could aggregate its data in exactly the same way as for classical data types, which means that the data chunks are processed in parallel by multiple CPU cores, and SIMD is used to process consecutive JSON path values in parallel. When we started out building true column-oriented storage for JSON in Clickhouse, we faced a couple of challenges. In Clickhouse, but also in any other relational database, table columns always have only one fixed data type. So accordingly, Clickhouse stores each column in a column file of the corresponding type. Depending on the column's data type, there may be many additional columns with metadata. So for example, nullable types in Clickhouse come with an additional column, which stores a null mask. And columns of type array are stored internally as two columns. One column stores the array values consecutively, the other column stores offsets to the starts of the individual arrays. This creates now three challenges which we needed to address. Challenge one is that you could end up with an avalanche of column files in scenarios with high cardinality JSON paths. These are scenarios where the stored JSON documents share no or only very few keys, leading to a high number of paths. Challenge two is that you need some sort of type unification when the same JSON path in different documents contains values of the same types. This is a problem because, as I mentioned, every column needs to be of exactly one type. And finally, challenge three is that some JSON paths could be much more frequent than other JSON paths. A rare JSON path would be mostly empty, except for a very few number of documents, which means that the corresponding column file would be basically hot air sparse. Now, if you didn't understand anything what I just said, don't worry. I'll give examples for each of the challenges on the next slide. Challenge one. Let's say we store 3 JSON documents. Now, if we start to insert more documents and each document contains a unique path, on the slide that's A, B, C, and D, Clickhouse would by default store each path in a separate column file, potentially creating an avalanche of such files. And this can be a performance problem. Think about it. The database needs to maintain a high number of file descriptors. Select queries would, need to do internal maintenance operations, and everything would become a lot more slower as we add more and more files to be opened and closed repeatedly. Challenge 2. Let's again assume a user inserted 3 documents into a JSON column. In these documents, path A is always of integer type. Now remember, all values within a path need to be of the same type. Let's now insert a 4th document in which our path A has string type. That's a problem. Perhaps we could get away if we cast the existing 3 integers to string. But if the user now inserts a 5th document, where A is a string array, it gets even more tricky. So again, we could force the existing values into their lowest common denominator. But what if such a type does not exist for some combination of types? So you probably think that we could always use a string as such a lowest common denominator, but that will make it extremely expensive to reconstruct the original values. All right, challenge 3. Again, we are storing 3 JSON documents. The user now inserts a 4th document with path C. Note that C does not occur in any of the other documents. So that makes C a rare path, at least compared to the other paths A and B. Clickhouse would create a so-called sparse column file for C. So that's a file with a single C value, but it's otherwise hot air. And you can imagine that is not very efficient. OK, now let's go back to the regular column-oriented storage in Clickhouse. The first building block that we implemented to overcome the 3 challenges is the so-called variant data type. On top of the slide, you can see how Clickhouse stores regular data. The example table has 3 columns, and every column goes into its own column file. With 3 columns and 3 rows, we have 9 values in the table in total. The important part is that the 9 values are of different type each. Now, the variant data type is able to store all the 9 values in one single table column. As you can see, it contains a mix of integers, strings, and arrays. But how does it actually store the values on disk? On the first look, the storage format looks familiar. It looks like traditional storage. All the integer values are stored together in an integer column, and all the string values in a string column, and all the arrays in 2 files. One file with the array values, plus one file with offsets to the array starts. What is new is the so-called discriminator column. It stores the data types of the values on each row. The discriminator column is printed in blue. Clickhouse assigns one discriminator value per data type. So a discriminator value is an index into a list of sorted type names. In our example, we have arrays, integers, and strings. So we sort these type names alphabetically. The array gets type index 0, integer gets index 1, and strings get index 2. The discriminator 255 is reserved for null values. So this means that by design, a variant can hold a maximum of 255 different concrete types. In gray to the right of the blue box, you see a second column, which is also part of the variant. This column maps each row of the discriminator column to the corresponding row in the subtype column file. Let's make an example. We would like to read the value of the variant in the third row. In the first step, we read the discriminator value in row 3. The value is 1. We now know that the value we like to read is stored in column file 1. Next, we read the value of the offset column on row 3, and the offset is 1. So the value we like to read is in column file 1 at row 1. And at that point, we can read 43 as the final value. Boom. The variant type solves challenge 2. We no longer need to store any sort of type unification for dynamic JSON paths. Additionally, the subtype data files are always dense. We don't store null or default values or anything like that. And that solves challenge 3. All right, that brings me to the second building block, which are dynamic columns. Under the hood, dynamic columns look almost the same as variant storage. The difference is that you no longer need to declare all the used data types upfront. Instead, as a user, you can simply insert different values with different types into a dynamic column. Clickhouse uses a metadata file to track all the used types together with some statistics which are used for maintenance operations. Okay, now we need to be careful to not create too many column files for too many dynamic JSON paths. The dynamic data type has an option to limit the number of data files that are stored on disk. So in this example, we set the max types option to 3 and start to ingest data. Clickhouse sees the first integer value and stores such values in separate column files on disk. And then Clickhouse sees a string value, and it stores the strings also in a separate column file for the same, and the same for arrays of integers. Now Clickhouse sees a fourth data type, dates, and a fifth type, boolean, and a sixth type array of string. And all these values are stored together with their type names in a shared data column. This mechanism solves our sub-challenge of too many columns for highly dynamic JSON paths. Okay, that was a ton of information, I know. Let's bring everything together. This slide presents the new JSON data type in Clickhouse. You are now able to create a table with a JSON column like this. The JSON type has 4 optional parameters, and remember, we still have an unresolved sub-challenge marked with 1. On the slide where we want to prevent an avalanche of column files for high cardinality JSON paths. This can be achieved with the max dynamic path parameter, which has a default of 1024. The value specifies the maximum number of JSON paths that are stored separately as dynamic paths. And that fully solves our sub-challenge 1. Then there is parameter max dynamic types, with a default of 32, which allows to restrict the number of data types which are stored as separate column files per path. You can also specify type hints, and these refer to static JSON paths, meaning that all the values have this same data type. Such paths are stored in the same way as classical data types. And finally, either directly or via regular expressions, you can exclude specific JSON paths from being stored at all. This can be useful if you know that you will definitely not need to store or aggregate some of the paths. Okay, let's look at an example. On the top, you see a Clickhouse table with a JSON column that has 2 type hints, max dynamic paths set to 3 and max dynamic types set to 2. As a reminder, max dynamic paths prevents that too many column files are created for high cardinality JSON paths, while max dynamic types prevents that too many column files are created for highly dynamic JSON paths. So let's walk through the paths one by one to understand where the data is stored on disk. The first path is a.b. Because we specified a.b as a type hint, the values from that path are stored exactly like a normal integer column on disk. The same happens for path a.c, which we also set as a type hint. The path a.d is our first real dynamic JSON path. The values of this path are stored in a dynamic column. And the path contains 4 different data types. Because we specified max dynamic types as 3, we only store the first 2 types as separate column files on disk. And all the values of the third and fourth data types are stored in the shared data column. Clickhouse then finds a.e, which is the second dynamic JSON path. And it stores it accordingly as a second variant column. And then we have e as the third dynamic JSON path. With that, we have reached the limit max dynamic path, which we configured to 3. So therefore, the values of the remaining JSON paths are stored together in a shared data structure, where we have a column for tracking table offsets, a column for storing JSON paths, and a column for storing the values of these paths together with their data types. And lastly, there is a metadata column which tracks all the paths with some statistics for efficient maintenance. Okay, now the big question is, was it worth to implement all of this? Did Clickhouse actually become the fastest analytics database for JSON data? Yes, it did. And to prove that, we recently introduced JSON Bench, the first systematic, fair, and vendor-neutral benchmark which focuses specifically on analytics over JSON data. If you Google for similar benchmarks, you will find that JSON Bench is truly the first benchmark for analytics on JSON documents. Like ClickBench, JSON Bench is an open source project on GitHub, and so far we have received 5 pull requests adding additional systems to the dashboard. On this slide, you see the current performance ranking in JSON Bench of databases with first-class support for JSON data. And as you can see, Clickhouse is in the pole position. Not only that Clickhouse is the fastest database, it is also the technically most advanced database when it comes to JSON. For example, no other database but Clickhouse supports dynamic JSON paths without any type unification. All other databases either force values into a common type or simply reject documents. As you can see, Clickhouse is significantly faster than established JSON data stores like MongoDB. Let's have a closer look at this. For example, to aggregate 1 billion JSON documents, the cold and hot runtimes of Clickhouse are 2,500 times lower than those of MongoDB. In this scenario, we tuned MongoDB to the maximum. For example, we enabled MongoDB's covered index scans such that the system didn't even need to load the JSON documents from disk. Speaking of disk, if we enable CSTD compression for the JSON documents, both in MongoDB and in Clickhouse, Clickhouse still needs 40% less space. What is even cooler is that the JSON documents compressed with CSTD in Clickhouse consume 20% less disk space than the original documents compressed with CSTD. This means you could use Clickhouse as kind of a JSON file system, even if you don't intend to query the data. So Clickhouse offers the most space-efficient storage for JSON documents possible. Actually, Clickhouse stores JSON documents more compactly than any other data store on the market with first-class JSON support. And this is my final slide about benchmark results. It shows the cold and the hot runtimes for the first query of JSON Bench, aggregating 1 billion JSON documents. Clickhouse achieves a throughput of 2.5 billion JSON documents per second with a peak memory consumption of only 3 megabytes. And all of this on a pretty normal server with 64 cores. That's all from me today. My message is that Clickhouse now speaks JSON. We completely reimaged the way how JSON is stored in columnar databases. And as far as we know, Clickhouse is the first database that stores JSON in a truly column-oriented fashion, unlocking performance gains like never seen before. Clickhouse is so efficient at storing JSON that its internal data representation is even more compact than the original compressed files. The implementation is easy to use, it's flexible, and of course it's extremely fast. It is many thousand times faster than traditional JSON data stores. And since March, this feature is GA. it's available in the Clickhouse open source database. Please test it out. We can't wait to hear your feedback. Thanks a lot.